Hello, welcome to the next lecture in the NPTEL series on Haskell. In the next few lectures, we will be looking at variants of trees, which is a very important data structure. We will be looking at binary trees, we will be looking at balanced binary trees, and we shall also be looking at another data structure built based on trees called heaps. All these are used to uh, process data in a certain way and assure some certain time complexity. Okay, so these are very versatile data structures and very useful in all of computer science. So it is good to know how to program these in Haskell. So a binary tree data structure is defined as follows. So this is an inductive definition. This is just like defining numbers. 0 is a natural number. If n is a natural number, successor of n. Yeah, you are giving an inductive definition of the type. So natural numbers consist of 0, successor of 0, successor of 0, etc. And you state that in this succinct manner. Similarly, tree, there are lots and lots of trees, we will see examples of those. You start with the empty tree. The empty tree is a binary tree. And if you already have two trees like n here, which is already a natural number, then you can form a new tree by putting together those trees and adding an element on top. A node containing an element along with a left subtree and a right subtree is a binary tree. Okay, so this is just an inductive definition. So how do you render this inductive definition in Haskell? Quite simple. You just say, we have already seen how to define data structures with multiple constructors, etc. Nil and node are two value constructors. And B tree is a type constructor. There is no necessity that you should only have binary trees consisting of integers or binary trees consisting of real numbers or whatever. You could have any type whatsoever there. No matter what your type is, so this is a collection data type. So you can also think of it as a collection, right? So normally you would collect elements of type A in a list. That is what we have seen, and that is the most ubiquitous in Haskell. But there are other ways of organizing your data. So this is a different collection of values of type A organized in a tree like manner. You are not organizing the elements of type A in a tree like manner, rather you are organizing your collection in a tree like manner. Okay, and what is this useful for? We will see. Yeah, so node is a value constructor, nil is a value constructor. Nil does not take any arguments. So nil, without taking any arguments, it will produce a B tree of type A. Note that this is all polymorphic. Node will take a B tree A, another value of type A and another B tree A as arguments, and the result will be a B tree A. Right. So we have already seen this. Constructors are nothing but functions. So nil and node are nothing but functions of these appropriate types. Okay. They will always produce a value of type B tree A. Okay. So the two value constructors are nil and node with these types, as I have just mentioned. Here are a few example binary trees, and here is how you would represent them in Haskell. Node of node nil 2 nil, 3 node nil 5 nil. Okay, so this part is node nil 5 nil. This part is node nil 2 nil. Let's call this TL and this TR. Then this whole tree, let me change color, the whole tree node TL3 TR, okay, which is what we have written. So, node, this is TL, this is TR. Okay, the overall thing is node TL3 TR. TL stands for tree to the left and TR stands for subtree to the right. And the root, so this is called the left subtree. In a tree like this is called the left subtree. This is called the right subtree, and that is called the root. Just to fix terminology. Here, this is an example tree. Here is another example. So, note that we are not imposing any order between the elements. I mean, I could put, this is a tree, equally validly I could have a tree which is like 3, 5 here and 2 there. Okay. Okay. And these nodes, these filled nodes denote nil. They do not have any value in between them, they do not have any value inside them, but they are just filled with a color, and that stands for nil. Okay. Here is another tree, here 6 is the root, this is the left subtree, this is the left subtree of the tree, and this is the this is the left subtree of the right subtree of the tree. This is the right subtree of the right subtree of the tree, and this is the root of right subtree of t. Right. So, you can think of these. So, here 6 is the root, to the left you have 4 and below that it is nil, and to the right you have a tree with root 3 whose left subtree is node nil 2 nil, whose right subtree is node nil 5 nil, and you can see that I have written it here, node of, this is the root, and this whole thing is the right subtree. And this whole thing is the left subtree. Okay, normally you will just to keep your pictures smaller, you will omit the nodes representing nil usually in the visual representation, not in the actual representation. When we draw trees, yeah, so then this is clearer to say 6, 4 to the left and right there is nil, 3, 2, 5. So, that's another tree. Okay. Here is yet another binary tree. You have 3 and to the left there is 1. It does not have any empty left subtree. Empty left and right subtrees for both these things. Here this is empty right subtree. Okay, that's another tree. Binary because there are at most 2 children. At most 2 children. Okay, and this B tree would be represented as node of nil, this is nil, 1, and this is node nil 2 nil, and the root is 3, and to the right you have node of node nil 4 nil here, and 5 is the root and the right subtree is nil, right. So, this is how you Okay. So now you can have, so now we have a recursive data structure. We know how to write programs using recursion on any inductive data type or recursive data type like this. So here are a few functions that we might want to write. Is nil, which will check whether a tree is empty. Size, which should return the number of nodes in a tree. Okay, and height, which should return the number of nodes on the longest path from root to leaf. Okay, so is null of nil is true, is null of anything else is false, right? So that's one program. Simple pattern matching recursion. Size of nil is 0. Size of node TLXTR is 1 plus size of TL plus size of TR, because there is one node which is the root. There are size of TL many nodes in the left subtree, size of TR many nodes in the right subtree. Height is interesting. Height is the length of the longest path from root to any leaf. So if your root is already, if your tree is nil, then there are no nodes at all, then you will say height is 0. If your tree is of the form node TLXTR, then you have the root, and then either the longest path from root to leaf lies on the left subtree, goes via the left subtree, or it goes via the right subtree. So you compute the height of TL, compute the height of TR, take the maximum of the two using this function max, and then you add one to it. And the one you need to add, because you pick the longer of the two paths and then you extend it by adding the path from root to that child, okay, either the left child or right child. Yeah, so the root of the left subtree for any node child is the root of an immediate subtree. Left child root of left subtree, and right child is the root of the right subtree. Just to establish some terminology in case you are unfamiliar with these things. Many of you might have seen this in some course or the other in your academic career, but in case you have not seen this, I am just recalling this terminology. In any case, doing this in Haskell would be new for all of you. So this is a good chance to, this is a very good exercise in trying to program with Haskell. You will see especially that the power of pattern matching is very well utilized in these exercises. Okay, so we can try to write other functions as well, but before we do that, I will take you to VS Code and we will see how these functions work on trees. I have already written a lot of programs here. So here is the definition of a B tree. Notice that I am not saying deriving show, because I will give a very special kind of show which will help you view the trees better. And I have these tree 1 and tree 2 are example trees. Node of node nil 2 nil. So the left subtree has 2, the root is 3, and the right subtree is 5. Tree 2 is node of the left subtree has 4, the root is 6, and the right subtree is the tree 1 that you have already seen. Let us try to see how these trees look. Yeah, so I am writing it in this list form just to visually make it easier for you to figure out. That is the root, and if I indent it within these square brackets, I am putting all the elements in the left subtree. So the left subtree is just one node 2, the right subtree is just one node 5, and this tree ends. Whereas tree 2 has the following structure: the root is 6, the left subtree is just the node 4, the right subtree has root 3, its left subtree is just 2, just the node 2, and its right subtree is just the node 5, right. So this is a very simple way of representing trees which will which is much easier to parse than if you just write node something something. You would have to write something like this otherwise. Node of nil 4 nil 6. So this is how you would have to write trees. Okay, and this is hard to parse. But I have written a so here 6 has left subtree which is 4 and both its children are nil. The right subtree is nil, so which I am denoting by putting a star. The star tells you that there is a left subtree for 6, but the right subtree is nil. So in such cases, I will put a star. I could also have left subtree and left subtree empty and right subtree non-empty like this. But then it would be displayed like this. The root is 6, the left subtree is missing, it's nil, but there is a right subtree. Okay. Okay, good. So this is how you display trees. Let's look at some of the other functions that we have written. Yes, this is is nil. Yeah, is nil of nil is true, is nil of empty list is false. So I can actually ask is nil of tree 1. It says true. Is nil of nil, it says true. Is nil of tree 1, it says false. Is nil of tree 2, also it should say false. Okay. Okay. So let's get back to the program. Size I have written. So size of nil is 0, size of node TL, and you don't even need to name the root. You don't care what the root is because that's not used in the program. Size of node TL underscore TR is 1 plus size of TL plus size of TR. And yeah, so it's always it's terrible if you have to keep writing trees as node of node nil to nil etc etc. So I will have some nice ways of creating a tree from a list. And one way of creating a tree from a list is what is called right skew tree, and another way is what is called left skew tree. I'll run these in GHCI and you will realize what these things mean. So right skew tree of 0.9 is a tree that looks like this. 0 is the root, its left subtree is empty, its right subtree has 1 as root, whose left subtree is empty, and whose right subtree has root 2 and its left subtree is empty. If you are to think of it as a picture, you will, I'll draw a picture when I get back to the slides. Similarly, you can do left skew tree. Now you will see that 0 is the root, its left subtree has root 1, its left subtree has root 2, its left subtree has root 3, etc. etc. all the way down. You have 8 here whose left subtree is 9, whose right subtree is empty, and 7 has left subtree this and its right subtree is empty here. The tree with root 6 has left subtree this, but its right subtree is empty, and so on and so forth. Okay. So you have left skew trees and right skew trees. You can have those. Let's look at what else I have programmed. I have programmed a lot of other things. Height is something that I have programmed. Height of nil is empty, is 0. Height of node TL underscore TR is 1 plus max of height TL, height TR. So I can ask, for instance, the height of right skew tree so it's 10. I can ask for size of left skew tree 0.9, that should also be 10. Yeah, here is a case where you have height is the same as size for right skew trees and left skew trees. You will later see that this is a kind of a bad behavior. You would like to maintain height to be as small as possible, and you can have actually height as small as possible. We will see examples of those. Okay. Okay, let me get back to the slides. We said, yeah. Okay, so here is a simple function that I want to write going beyond size, height, etc. Reflect the tree on its vertical axis. What do I mean by that? What I mean is this. If I have a tree like this, 6, 5, 6, its left subtree is 4, its right subtree is this 3, 2, 5. I need to think of a mirror like this, I want to flip it like this. What would happen is that the left subtree would become the right subtree and the right subtree would become the left subtree, but not the right subtree, that also should be reflected. So, the reflect of the right subtree should become the left subtree, okay, and the code is simple. So, yes, so this should become this 6, 4, 3, this thing should become actually the left subtree which is 4 became the right subtree, and the right subtree which is 3 with 2 on the left and 5 on the left gets reversed and it gets moved to the left. So, the program is simple enough. Reflect of nil is nil. Reflect of node TL x TR is node of reflect of TR x reflect of TL. Okay. Okay. So, you should check that if I take a left skew tree and reflect it, it will become a right skew tree and vice versa. Here is another function that I want to write. This is a kind of a depth first exploration of the tree. Breadth first exploration of the tree. What I want to do is the following. I have a tree, I want to list all the nodes level by level and from left to right inside each level. An example will help. So, let us look at the tree here. 3, so the way I should list this is 3 first and then 1, then 5, then 2, then 4. I should list it level by level, right. This is the first level, second level, third level. So, levels of this tree should be 3, 1, 5, 2, 4. This is a very interesting exercise where you get to use some things that we have already done, namely queues. Okay. So, the simplest way to do would be to maintain a queue of trees. So, initially you have the whole tree. Let us give name to these trees T, TL, TR, TLR, so there is a TLL which is nil, and there is a TLRL and a TLRR, these are also nil. There is a this is TRL. When I say TRL, I mean the tree whose root is 4. Okay. So, TRL, it has a left subtree which is just nil, TRLL, and similarly you have TRLR which is also nil, and then you have a TRR which is nil. Okay. These are all the trees here. Okay. So, now you will maintain a queue of trees. What do? You will start with T, this is your queue. I will write the queue in list notation, but that is okay. I will change color and do this. You start with this T, then at every point what you do is you dequeue from the queue, take the first element and remove the first element. So, you have to print somewhere in a list you will print 3, you will print the root of the tree, the first element is t, which is whose root is 3, and then you will remove this from the queue. So, I will write the evolution of the queue and what you will print. So, you start with this, then you will remove t from the queue and you will put TL and TR in that order. Meanwhile, you would have printed 3. Now, you have TL, that is the first element, you will remove that and you will put its left child and right, its left subtree and right subtree, but only if the subtree is not nil. So, you check the left subtree, it is nil, so you do not touch that, you do not go there at all. So, there is only a right subtree. So, what you will do is you will put TLR. Where will you put? You will put it at the end of the queue, because you want to maintain all this in queue order. So, you remove the element from the queue, it will remove it from the head, you add an element to the queue, it will add it at the end. So, now you have TR, TLR, and you would have printed the root of TL, which is 1. Okay, not printed, you would have put the root of TL, which is 1 in some output list that you want to create. Okay, now you will once again look at the head of the thing. So, you have TR, TR is its root is 5. So, but you would remove TLR, you would remove TR and put in TRL and TRR, but TRR is empty, so you do not put that in. So, you will say TLR comma TRL, because you have to put the new element at the end. Okay, so that is this. Now, you go to TLR, both its children are empty, so you will just remove TLR, add its root to the output list, but there is nothing more to add to the queue itself. So, TLR gets removed, you will just have TRL, and you have 3 followed by 1 followed by 5 followed by 2, and now TRL, both its children are empty, you will just put its root in the output list and remove this. So, now the queue becomes empty. When the queue becomes empty, you stop and you have an output list which is 3, 1, 5, 2, 4, which is the correct order of the thing in the levels. This is what you want, 3, 1, 5, 2, 4 is what you want. Okay, this is what the algorithm will look like. Here is the implementation. I will import the queue methods, and levels of t is some go is some local function I am defining, local auxiliary function. Okay, and what do I do? I start, this is the empty queue. And I am defining a new operator. This is a smart enqueue. Let me say. Why is it smart? It will enqueue only if the tree that I want to enqueue is non-nil. If it is nil, then I won't do anything. Okay, so that is what this does. Q plus equal to t, not plus equal to, plus colon t. If is nil of t, then don't change the queue. Else enqueue the tree t in the queue, inside the queue. Okay, good. So that's that. And what is Go? Go is a recursive this thing. It will implement what I told earlier. What it does is, if the queue is empty, then you just return the empty list. Else, you first do. I mean, what Go should produces a list from a queue of B trees. Okay, that's what it does. So, if the queue is empty, then you just, there is nothing to produce, you just produce the empty list. Else, you look at the first element, you dequeue the queue and you will get one tree we have a guarantee that all trees in the queue are non-empty, because if the tree is nil, we don't enqueue it into the queue. So, this queue will be non-empty, it will have structure node TL XTR, and q prime is the remaining queue after you dequeued it. Now, what will you do? You will you will just publish X as part of the output list, and then you will try to produce a list from this modified queue, which is q prime. Q prime is T removed, and then you will add TL and TR to the end of q prime. Okay. Okay, so this is the program, and this is what you might also call, and in fact, I should have called it breadth first listing. Okay. Okay, so this is a program that prints things level by level. We will look at examples of all these once we have some means of creating trees in a convenient manner. Okay. Let's at this point I will go to the code and show you these levels and how it works. Okay, I've added a routine which produces a random list of whatever many numbers you ask for between -200 and 199. So, it's very convenient that we have already seen random RIO, replicate M, etc., so that you can actually create these things to test your data structures. So, I'll go to GHCI and I'll reload this thing. Now, I can ask for XS is some randoms of size, a random list of integers of size 20, let us say. Yeah, so that's a random list of integers. Now, I can actually ask how to create a list, right. So, I can create a tree. I have written a routine which we will see later about how to create a tree from a list. And in fact, this format doesn't, it's not very helpful if I have, so let me just use 10 elements. XS is this. I can say T equals create tree of XS. And if I try to print T, it will look like this. See, this is actually a random tree because it is not skewed to the left or to the right. If I have to draw this, this is -192 is the root. Its left subtree starts with -71 and there is 39, -176, whatever. So, you can see that this is a tree. Later, I will show you a better method for rendering trees, which will actually render it like a tree. In fact, I can actually do it right now. So that you have a better way of viewing these trees. Just a couple of minutes before I correct this, and then okay. So now we have written this. Let's try whatever we were trying again. X is randoms. Let's say some 20 random integers. Let's look at the list. So it's just a list of 20 numbers between minus 200 and plus 199, and I could do a create tree x's, yeah, and you can actually see the tree being drawn. Okay, minus 185 is the root, and I'm just creating a random tree, but this tree is of some limited height. Okay, that is fine. Now what did I want to do? I wanted to, so if I want to do the breadth first listing of this, what would it be? It would be minus 185 followed by minus 130 followed by 162 followed by 78, minus 78 minus 148 minus 175 minus 120, etc. Let us just check that breadth first list of okay. So you see that this program actually works correctly. Minus 185, then minus 130 minus plus 162, then 78 minus 148 minus 175 minus 120, then you have minus 120 again, minus 35 minus 172, 90 minus 58 137 minus 112 plus 199, and then finally you have 68 58 minus 107 minus 29 minus 121, right? So yeah, so this is one of the first non-trivial programs you have written concerning lists, concerning trees, binary trees. Let me now get back to the slides.